the concept of conditional probability, and we had also introduced Bayes' rule. In this lecture, we will first start with Bayes' rule, and then we will continue to see how the probabilistic reasoning can actually be implemented using the notion of conditional probability. So, to start with, we have a revisit of the Bayes' rule. As you can see here, that I want to know the probability of A given the probability of B's occurrence. So, when I know the probability of occurrence of B, how would I compute the probability of A occurring? Now, that is expressed in terms of a priori probabilities of B and A, and also the probability of B given A. So, here we are trying to compute A given B in terms of the known probability of B given A, and here is an example of how we compute that, and that was done in the last lecture also. The a priori probability of the doorbell ringing is 0.001, and the a priori probability of Mohan's waking up is 0.01, and a priori probability of waking up given the doorbell ringing is 0.8. From there we compute the probability of doorbell ringing given Mohan's waking up as using Bayes' rule 0.8 times P d divided by P w. So, we get 0.08. This is the basic notion of Bayes' rule. Now, as we have said earlier also, that such conditional probabilities are applied when the two events are not independent. Okay. If two events are independent, say A and B, two events are independent, when do I call them independent? Now, in terms of probability, in terms of conditional probability, if A and B are independent, then P probability of A given B will be the same as the probability of A, because A and B are actually independent, and probability of B given A will be the probability of B itself, because they are independent. Therefore, in case of independent events, the joint probability, the P A and B is P A times P B. Now, here we can see a simple scenario that the probability of A given B is 0.2, probability of A given not B is 0.3, probability of not A given B is 0.1, and the probability of not A given not B is 0.4. It is interesting to note that since they are joint probability, the sum of all these are coming to 1. Okay. Now, we have seen therefore, here that there are some nice formulations about computing the probabilities of events. We can compute the probability of A if we know the probability of B in terms of Bayes' rule. However, and that is very much applicable in the case of rules where we deal with event E leading to hypothesis H. So, probability of H given E can be computed similarly, but there are of course some advantages and also there are some problems. For example, the advantages are that since it is based on the probability theory, which has got years of formal mathematical foundation, it is very rigorous, and it is reflection of a reality, because we are computing a posteriori probability. Now, the word a posteriori is just the opposite of a priori. A priori means something that is known beforehand, and a posteriori is something that we are trying to know, and that is very much evident in the case of Bayes' rule, as we had done, that we want to find the probability of this, that is, we want to find the probability of H given E. We want to know this. We know the probability, a priori probability of E, we know the a priori probability of H, and we also know the a priori probability of H E given H, that is same as H leads to E. If we know these from, these are known a priori, these are known beforehand a priori, right. And using Bayes rule, using these three, we are computing this one which is a posteriori. All right. So, that is a very nice thing to do. Now, however, there are some inherent problems in the case of probabilistic approach. What is that? The problems are that it may be inappropriate, because the real world scenario is changing. Therefore, the future may not always be similar to the past. So, we are taking a priori probabilities which are based on the past information, and we are going to predict the probability a posteriori, that is a futuristic probability, but that is valid as long as the world does not change. But in reality the world is changing, and therefore, this may not be appropriate always, number one. The second thing is that it may be inexact or incorrect, especially for subjective probabilities. If we compute the probabilities based on a large number of experiments that we do, that is fine, no problem with that. But in many cases, we cannot carry out so much experiment for all the rules, and therefore, we often have to go by some subjective measures and subjective inputs, and that is where the inaccuracies may creep in. So, in order to apply it rigorously, the probability the probabilistic reasoning rigorously, we need to carry out a huge set of experiments to find out all the possible of conditional and joint probabilities, and that is really an overhead, because if there be n events, then for all possible combinations we need to find around 2 raised to the power n number of probabilities. The other thing is that knowledge may be represented implicitly. In that case, we cannot really find out the probability corresponding to this. Now, the Bayesian approach, in spite of now just to avoid these overheads, say this overhead of finding out objective probabilities always, and the huge amount of computation that is required, we sometimes feel like bypassing this computational overhead and take recourse to some subjective measurements and have a quick but good enough solution. And that is why the certainty factor approach that we have seen in mycene tried to avoid this overhead of the probabilistic approach or the Bayesian approach, and take recourse to some subjective measurements and certainty factor algebra, which assumed that the events, all the probabilities which are dependent causally should be clubbed together in a rule, and we will be dealing with only independent events. Then the computation becomes much simpler. However, Bayesian approach demands discussion in its own right. In Bayesian approach, the basic tenets or the steps are these. We first derive the probability of a cause given a symptom. Okay? We get a symptom and we want to find out the probability of the cause. Now, this has although it required a lot of computational power, but now it is gaining more and more importance because we are having more and more powerful machines. So, more computational power being available and better algorithmic methods being available, Bayesian approach is becoming more popular, very much in the case of machine learning, information retrieval, and language processing, etc. The Bayesian approach is especially useful in diagnostic system like medicine and computer diagnosis, etc., because we are trying to find here the basic thing is we are trying to find the inverse or a posteriori probability, that is inverse of the conditional probability of an earlier event. Okay. given that a later one occurred. Now, we will just see that Bayes theorem, as we had presented earlier, needs a little bit of extension when there are a large number of hypotheses. So, here let us see, let the evidence E be there with some probability. We want to find the probability of a hypothesis, a particular disease, given a symptom. Given this evidence, what is the probability of a particular hypothesis HI? So, that is the probability that hypothesis HI is true given the evidence E. And here we are having the a priori probability known beforehand, that probability that will always observe the evidence E if the given that the hypothesis HI is true. If the patient has malaria, then always there will be fever. What is the probability of that? PHI is the a priori probability that the hypothesis HI is true in the absence of any specific evidence. As I said, I go to a particular village and I straight away know that 60% of the people suffer from malnutrition. So, for that I need not really do a lot of statistics. For that I can simply, if I have got that data, I can start with that PHI is probability that somebody in that village will suffer from malnutrition is 0.6. Now, there can be, now we have got an evidence E which can support a number of hypotheses, n number of or k number of hypotheses, all right. Now, for that, then this evidence E and its contribution to a particular hypothesis is distributed over all these k hypotheses, right. So, Bayes rule or Bayes theorem needs to be modified in this way. PHI given E is P of EHI, that was there already, the a priori probability of the evidence given the hypothesis times PHI divided by all the, say, n varies from 1 to k, because I am talking of k hypothesis, then P EHN, E given HN times PHN. So, I am here, earlier I was dividing, if you just have a look at Bayes theorem, I was just looking dividing by this evidence part, or rather the B part. Okay. Now, in this case, this will be divided by all the possible hypotheses that I know of. So, I am coming to this notion. So, this is a general structure of Bayes theorem, that is why we are calling it as extended Bayes theorem. Next, let us look at an interesting example which will reveal to you the interaction of the causes and effects. If you will see that a particular cause leads to an effect, or a particular cause can lead to two possible effects, and there is a very nice interaction among them. Let us look at this. Let us see, S means the patient has spots or rashes, all right. M means the patient has measles, and F is that the patient has high fever. Now, look at this causal diagram. If the cause is measles and measles leads to spots, measles leads to fever. Okay. Both of these are effects. Now, suppose I observe the evidence spots. Now, these spots, although it is an effect of measles, obviously it will serve as an evidence for measles, but it will also serve as an evidence for fever, though there is no direct causality here, but the causality is coming in an indirect way, because if somebody has spots then he or she may have measles, and if he or she has measles, he may have fever. So, that is the way in which the evidence, this evidence is also affecting, it is serving as an evidence also for fever. All right. Now, assume that, so in the earlier case we had assumed that my evidence was spots, spots was known. Next, I see that measles is known, the disease is known, that somebody has measles. Now, obviously, if somebody has measles, then if it is known, then obviously we can infer this evidence that he will have spots. Okay. And once we infer spots, then that is also supporting fever, okay, because then this is again serving as an additional evidence, increases the belief in favor of fever. If I know this, then of course I know this. So, what happened is, if I start with spots, I know I can infer measles as a causal, or I also increase the belief in terms of fever. If both spots and fever are present, I mean they could be present independently, no problem. But if both of them, spots and fevers, are present, they provide they provide evidence in favor of measles. But unfortunately, they are not. If they were independent, I could have combined my beliefs of spot leading to measles and fever leading to measles, all right, independently. That would be something like this. Say, or I'll not say, I know that okay, spots, no, I will just do it in this way. Measles, if someone has measles, he will have spots. If someone has measles, he will have fever. So, using Bayesian, if I know this, then I can also, I know spots independently, I know fever independently. So, I have got two evidences, E1 and E2, and both of them are pointing to hypothesis H. That would be a joint probability which we could have done. But unfortunately, if E1 and E2 are independent, but unfortunately, as we have seen in this case, spots and fevers are not independent, because E1 is related to H and H is also related to E2. So, there is an unseen dependence here, and so these are not dependent. Therefore, I cannot straightway combine them, which I could if they were independent. So, we cannot simply sum their effects, but we have to take conditional probabilities of their conjunction into account. Okay. So, in general, given a prior body of evidence E and some new observation E, capital E, we have to compute P H. So, this is a new observation, earlier observation was this. So, you see what happened, I knew that he had spots. So, I had inferred something about measles. Now, I know about also fever, this small e is fever. That means, now I have to compute this conditional probability as P H given E times P, this is the dependence, that if somebody has spots and measles, then what is the probability of his fever? I have to multiply with this and then divide with the dependent probability, conditional probability of fever when somebody has spots. So, you see, I need to find so much, I have to find out this conditional probability as well as this joint probability, and in a real world the size of joint probabilities that we need to compute grows as 2 raised to the power n if there are n propositions to be considered. And that is the real problem for dealing with Bayesian applying the Bayesian approach. However, in order to facilitate our computation, some intelligent techniques have been devised. Now, we will talk of one such technique, which is known as belief network. What is a belief network? I will first define them. So, slowly you should try to understand the nuances of this definition. A belief network is a representation of causal connections between different events with associated conditional probabilities. Let me first show you a picture of a belief network. It looks like this, that all the nodes of a belief network, forget about these tables right now, all these nodes are basically events, and two nodes are connected by an edge if one node is the cause of the other. This is a typical example of a burglary, burglar's alarm case. Okay, I will explain this problem, but look at this, that alarm, this event has got a parent burglary. That means, burglary will cause the alarm, earthquake is another parent. So, earthquake will cause alarm, and each of these edges show that there is a causal relationship. Now, so nodes are representing events, and that network is a representation of causal connections between different events. Directed edge from one node to another, node A to node B, represents the fact that event B may be, please note, may be an effect of the event A, and we are storing conditional probabilities for a node, and conditional probability for a node is provided for each possible value of its parents. Okay. That means, again let us come here, say the conditional probability of A, say think of this alarm is being given, I am sorry, say for this node John calls. What is the probability of John calling? That is given for, or what is the parent of John calls? Alarm. So, I am giving the, in the belief network corresponding to this node John calls, I am giving a list of probability table, a probability table with a list of probabilities of John calling for every possible value of the alarm. The alarm may ring, that is true. In that case, John calls is 0.9, and if this is false, it is 0.05. See here, for this conditional probabilities, it may not add to 1. Okay. Now, with this definition, now let us come to this example. There is a burglar's alarm fixed at home. Now, this burglar's alarm is fairly reliable, and that means whenever there is a burglary, the alarm will ring. If a burglar breaks open your house, it will start ringing. However, it is not 100% accurate. It also responds at times to minor earthquakes. Whenever there is a minor earthquake and the door is shaking, then also it starts ringing, but that is a minor scenario. The other thing is that there are two neighbors who on hearing alarm calls the police, John and Mary. Now, John always calls when the alarm rings. John is very particular about it. If the alarm rings, John will call the police, but sometimes he confuses the telephone ring with the alarm, and even if there is a telephone ring, he thinks that it is an alarm and calls the police. That is his problem. And Mary has got the habit of listening to loud music and sometimes misses the alarm altogether, just misses the alarm. Okay. But if she gets the alarm, then certainly she will call the police. That is the scenario. Okay. Now, so here is the corresponding belief network: burglary, earthquake, alarm, John calling, Mary calling. These are the possible events, and for each event we have made a node, and for each of these nodes, burglary we have put an a priori probability of burglary as 0.001. An a priori probability of an earthquake occurring is 0.002. Now, alarm may be caused because of the burglary or because of the earthquake. So, if both of these things happen, then the probability of alarm ringing is 0.95. If burglary occurs and there is no earthquake, then also with 95% accuracy it will 95% cases it will ring. If there is an earthquake, then also sometimes it rings 0.29, and if none of them is there, then also sometimes for spooky reason it rings. So, this is the probability of alarm ringing with respect to these conditions, burglary and earthquake. But here you see these two which have got no parents are a priori probabilities. Now, what is the probability of John calling? You know, John, if there is an alarm, he calls, but sometimes he also calls when there is a telephone ring. So, no alarm, but he has called. And for Mary, if there is an alarm and she really gets it, she will call, but sometimes even if there is no alarm, she calls. So, suppose this is the, so this is associated with this node, this is associated with this node, like that I have formed the belief network. Now, let us quickly look at some of the properties of the belief network. As we have seen, a belief network is a directed acyclic graph, or in short DAG. There is no cycle in the graph, as you have seen here. Okay? Because in that case there will be a problem. If John Collins again starts burglary or starts alarm, then there will be a problem, it will be much more difficult to handle. Nodes which have no parents have prior probabilities, as we have just now shown, that the nodes which have got no parents have got are given a priori probabilities. All other nodes have been given conditional probabilities. In general, there can be multiple directed paths between a given pair of nodes. It is a possibility that there will be a multiple path from say one node to another, but that case we will not consider. We will consider the case when there is only one directed path or only one path, I would say, between any pair of nodes, and that scenario is known as a polytree. Okay, that is known as a polytree. So, I will show one polytree first before say a polytree. What is a polytree? A polytree is a graph where there is at most one indirect path between any two nodes, actually any pair of nodes. Okay. So, between these two nodes there is only one path either here, and why is it undirected? From this node to this node also there is only one path, whereas you see that this is not a polytree, because from this node to this node I have got two paths. All right. Again from this node to this node, here of course there is only one path, but from this node to this node I have got two paths like this. So, this is a polytree and this is not a polytree. We will restrict our cases to the only the cases where it is a polytree. All right. Now, given this scenario, which you can see that it is a polytree, now it is a polytree, what is the probability? We will see how to handle this. What is the probability that the alarm has sounded? Alarm has sounded, but neither a burglary nor earthquake has occurred, and both Mary and John has called. That means, I want to find out the probability here. In this case, John has called, Mary has called, but burglary and earthquake, none of these things occurred. Now, obviously, John has called because, is it just when there was no alarm, or John really heard that there was an alarm? What is it? Was there an alarm, or it was a false thing? None of these things occurred. How would I reason about it? So, I am trying to model this scenario. Probability that there was no earthquake and there was no burglary and there was alarm. Okay, the alarm has sounded, John called and Mary called. This is the probability that I will have to compute, right, and that is equal to probability of John calling on alarm multiplied by probability of Mary calling on alarm, probability of alarm ringing when there was no earthquake and there is no burglary, and the probability that there is no earthquake, a priori probability, and the a priori probability that there is no burglary. Now, in this graph poly tree, we have got all these values, all right. So, we will compute this from the same formula. We can see that probability of John calling on alarm was 0.9, probability of Mary calling on alarm was 0.7, probability of alarm being caused when both of them. Now, please look here, again I have to go back to this scenario. Probability that the alarm has occurred when there was no burglary and when there is no earthquake is this 0.001, right. This figure I will have to take, and times when I take this joint I have to take 1 minus 0.002, all right. What is that? That is the probability of not E, because the probability of E was 0.002 and probability of burglary was 0.001. So, the probability of not burglary is 1 minus 0.001, that is the basic of probability. So, we find the value as 0.0062. That is how we compute in the case of using the belief network. Now, we can skip a couple of definitions here. Now, if the information about the parent node is not known, then a node may not be conditionally independent from its ancestors. Okay. For example, if it say in general in a belief network, I will consider the conditional probability for the nodes which have got some causal relationship. Those which are not related, I will not consider them. Say for example, if I know, if I am in a scenario where I know that burglary has got some relationship with alarm and earthquake has got some relationship with siren, some other thing which is not related, and then therefore, in this graph I will just restrict myself only if there is to the nodes where there is a conditional dependence, and over here John calls, etc. Only for this I will not consider these nodes. But if I do not know anything that burglary occurred or John called, if for this event I do not have any information about its parent, then any of these can be participating in the decision making. Okay. Now, our problem was that in the case of Bayesian approach, we have to compute a huge number of probabilities. So, in a belief network, there are so many nodes and edges. Which are the paths that we have to really look into and take into our computation? In order to reduce the size of computation, we can very intelligently restrict ourselves to a subset of the belief network. In order to appreciate that, first let us look very carefully into these definitions. A set of nodes E, some set of nodes E, deseparates please accept this term, D separates two set of nodes x and y if every undirected path from a node in x to a node in y is blocked given E. Okay. Note it down, a set of nodes D separates two sets of nodes x and y if every undirected path from a node in x to a node in y is blocked given E. That means, say here is a belief network. Malnutrition leads to underweight, malnutrition leads to lack of iodine leads to goiter, and hormonal imbalance also leads to goiter. Now, you see this node is very critical, because this node deseparates this node and this node. You see why? What is this? Suppose if this node, I know that there is lack of iodine, then in order to reason whether he has got goiter or not, it is sufficient for me to look into whether hormonal imbalance is there. I need not look into malnutrition. But unless I identify this, unless I know this, then obviously I could have tried with goiter, whether he has got malnutrition. From there I would have started to reason. So, I would have needed more conditional probabilities to be computed, but in this case I can simply separate out between two sets of nodes x and y, okay, which are basically deseparated by this node lack of iodine. Okay. Another example, let us see. If I know that somebody has malnutrition, then I need not bother to reason about underweight. For reasoning about underweight, I need not look into the probabilities of lack of iodine, hormonal imbalance or goiter. Similarly, for finding goiter, I need not take underweight into consideration. So, this node is deseparating, is making two clusters, this one and this one. Okay. So, again lack of iodine is again clustering these. Now, let us go back to the definition. Now, we will understand it better. A set of nodes deseparates, say in this case that lack of iodine was the case or malnutrition was the case, which deseparates two sets of nodes x and y if every undirected path from x to y is blocked or goes through E, right, as was the case here. Every node from here, from this set, was going through this. There was no node which was bypassing this, right. Now, when we say blocked, I have just now said that is blocked. When is it blocked? A path is blocked given a set of nodes E if there exists a node Z in the path for which one of the following holds. Z is in E and Z has one arrow on the path leading in and one is leading out. That is this case. This is the node which is in E, that is it, that I know, all right, and that is a blocking node. So, there is one edge coming in, one edge going out. That is the first condition. Another case is Z. So, what is that? That Z is the node that is given a set of nodes E. Z is in E and Z has both path arrows leading out. Both the path arrows are leading out. This is the example. Z is in E. In my evidence set, Z is there, a particular node is there, and all of them are going out from here. So, obviously, the descendants of this are separate. Okay. The third case is neither Z nor its descendants are in E and both path arrows lead in to Z. So, that Z is the sink, both the path arrows are coming to Z. This is the case, all right. This is the evidence. although this is the evidence, but the blocking node is this Z, which is separating out. Why? Both the path arrows from here, from these clusters, it is coming into this to goiter. So, goiter is blocking out these two. All right. So, there is no dependence between these. So, this is a nice idea of deseparation, and therefore, I can restrict myself to my the computation of the probability with respect to the deseparated clusters only. Okay. Now, it is very important how we build in the belief network. When we build the belief network, we have got a number of variables. We have to select the variables in such a way that we will get good node, or it is possible, it will be possible to create deseparated clusters. So, that for our reasoning the computation of conditional probability becomes less. So, we choose the set of variables that describe the domain, like all those malnutrition, goiter, all those were the lack of iodine. These are the basic nodes, or for burglar's alarm you can think of burglary or earthquake, alarm, John calls, Mary calls. These are the variable set that I have to define. Choose an ordering for the variables, that is very important step, because I will first pick up a variable x and a node for it and set the parent of x to some minimal set of existing nodes such that conditional independence is satisfied. And then I will go on doing this, and in this way I will define the probability table for x. So, say given this, I have to select. Now, these are the possibilities. Now, I will first select one node and say I select lack of iodine, then I will have to select the parent in such a way, so that there is, I can create a conditional independence set, and then we define the probability of this. So, that is the ordering is very much important, and this approach is based on the minimalist principle. There is a smaller explanation, this is a very general philosophical term and is also applicable to AI. We can see that a smaller explanation should be preferred rather than increasing the number of premises. Say x has happened because A has happened, B has happened, C has happened, D has happened. Instead, if we could say K and P happened, and therefore, A happened. All right. So, that is the minimalist approach, and that is exactly what we are trying to do, that smaller the network, the better it is, both from explanatory and as well as from computational aspects. So, in order to really find a good belief network, we have to choose several orderings of the variables and construct the belief network incrementally, and ultimately keep the one with smallest number of edges. Okay. So, that is a very important step. Now, how do we infer in belief network? The inferences in belief network can be divided into 4 categories. One is you see diagnostic inferences. That means, from effects we want to go to the causes. All right. Suppose given that John calls, what is the probability of the burglary? So, the evidence was John has called, and what is the probability of burglary? That is a diagnostic. So, I have seen the effect, my car is not starting. What is the probability that there is some problem in the spark plug? That is what we are trying to do. So, it is diagnostic. What is the probability of burglary given John calling? The other thing is causal inference, okay, from causes to effects. Given burglary, what is the probability that John will call or Mary will call? There is a probability of John calling given B. For example, if I have if my spark plug of my car gets dirty, what is the probability that it will not start? That is causal. All right. The other thing is, the third type is intercausal inference. One common event can be driven by multiple causes. For example, alarm could be caused by burglary as well as earthquake. Given alarm, what is the probability of burglary? So, but alarm can be caused by both earthquake and burglary. From there, I want to, if one is known, then what is the probability of the other one? So, I know given alarm, what is the probability of burglary is, I know probability of burglary given alarm. Now, given earthquake, what is the probability of burglary? Okay, alarm has been there. So, probability of A and D, what is the probability of B? The other thing is mixed inference. Some things are causes and some of the effects are not known. For example, I know John has called, that is an effect I know, and I also know that no earthquake has occurred, that is some cause I know, the status of some cause. What is the probability of alarm? There is the probability of alarm when John has not called and there is no earthquake. So, figuratively we can see there are 4 patterns. This is a diagnostic. I know this evidence is known. What is the probability of a particular cause to have occurred? Causal is, I know that the voltage has increased. What is the probability that the current flow will increase? That is probability 1, but say I know the cause that burglary has, with some probability burglary has occurred. What is the probability that John will call? The third is intercausal. Something has happened and I know there are multiple causes. I know some probability of earthquake occurring, and I also know the relationship, the probability of alarm being sounded on earthquake. What is the probability that burglary has also occurred? So, there are multiple causes. I want to find this one. The other one is mixed inference, that is, I know some of the causes like and some of the effects. I know that John has called, I know that there has been no earthquake. What is the probability of burglary? So, that is mixed inferencing. So, there are 4 patterns. Now, polytree we have already explained. Now, the crux of this one I will try to simply explain. Say, let us consider x to be a query variable. We want to know the probability of x given an evidence E. So, I know the probability of E and I want to know the probability of x given E, and suppose and x is my query. So, I want to know the probability of x given E, and suppose there are a set of nodes which are parents of x and a set of nodes which are children of x. So, I want to know the probability of this. I can separate out, there can be some parts which are not neither parent nor children of x. X is the query variable, okay, whose probability, conditional probability I want to know. So, we separate out these two, all right. So, I call one to be E x plus, another one is E x minus, these two sets, okay. These are the effect set and you can say this is the cause set, all right. So, E x plus is a set of causal support for x, that is the variables which are connected through its parents, which are known, whose status and probabilities are known, and E x minus is a set of evidential support for x, that is variables below x are connected through its children. Therefore, now I can compute probability of x given E is probability of x I want to compute given E x plus and E x minus, because you see E x plus and E x minus, because other parts of the polytree are independent. How could I find out which are the independent parts? Because I have found out some nodes by which I could deseparate the entire belief network. Now, I have restricted myself only to a cluster after deseparation, the other part is not important. So, I have reduced the number of variables and therefore, I have also reduced the number of parents and children, number of children corresponding to a particular node x. So, I have got a smaller set of E x plus and a smaller set of E x minus. Now, we can simply apply Bayes theorem that probability of x given E can be computed as probability of E x minus given x and E x plus times probability of x given E x plus divided by probability of E x minus given E x plus, that is standard Bayes theorem. Since x is deseparating E x minus from E x plus, here you see x is also deseparating these two clusters, right, because all of them are coming through x. Therefore, I can further simplify it from this Bayes theorem part. We can say P x e will be, we just take the numerator P E x minus given x and P x given E x plus, and we multiply it with alpha, where 1 minus alpha is the constant representing the denominator, because they are deseparated, all right, E x plus and E x minus are deseparated, and so I can find out the independent a priori probabilities of this are useful for this. So, basically if they are independent, then probability of E x minus given E x plus is basically the probability of E x minus. If they are independent, then only this part is there, and this independence is coming from this deseparation, all right. Now, both the terms P x given E x minus and P x P of E x plus given x can be computed recursively using the conditional independence relations. Now, that is a simple way of dealing with the thing. Now, I will show you one simple example which will be a part of. We have shown 4 types of inferencing. I will first show you an example of causal inferencing and leave another diagnostic inferencing for you to do, all right. So, let us see the causal inferencing. What does it mean? I know that there has been a burglary, I know the cause, I want to find the probability of the effect. So, that is my query. So, this green part, burglary I know has occurred. So, that is my evidence, and I want to know the probability with which John called. How do I compute this? Obviously, I will have a deseparated graph and I will compute it here. Out of this, what is E x minus and what is E x plus? E x minus is, for this query node there is no children, x is, I mean this is my query node. So, this is my node x. So, there are no children. So, E x minus is null, and what is E x plus? E x plus is J is in E x plus, all right, John called is in E x plus. So, we need to compute probability of John calling given burglary. Now, this alarm is deseparating B and J, okay. This alarm node is deseparating these two, all right. So, using the Bayes theorem, we can write A can be true or false. So, probability of John calling given burglary, that is what I want to know, is probability of John calling not A given no alarm, probability of no alarm given B given there is a burglary, plus the probability of John calling given the alarm and the probability of alarm given burglary. So, using this, so you see I am just restricted, I have restricted it to 3 nodes of the graph and I can compute it as 0.858. Now, this is a simple way, not although even after this reduction there may be considerable amount of computation, but this approach. So, what is the fundamental thing is apply Bayes theorem, Bayesian approach, but form the belief network and then try to find out the deseparated part and only restrict yourself to this E x plus and E x minus sets and compute the Bayesian probabilistic value based on these nodes. So, that is the basic approach of belief networks or Bayesian networks. Now, to complete, I am just giving you the example of causal reasoning we have shown, causal inferencing. So, here I am just posing this problem to you as a quiz, as a test. You can try this. Here, the scenario is John has called. So, it is diagnostic. What is the probability of burglary? John has called. What is the probability of burglary? That is the thing we want to find out. Try to solve this problem and then you will have a nice confidence about applying Bayesian networks for managing uncertainty. Now, these are some of the approaches. So, we have seen certainty factors and we have seen in quite detail the probabilistic approach and the Bayesian approach. In the next lecture, we will see another way, another method of handling impreciseness type of uncertainties. We will discuss fuzzy set theory and fuzzy logic in the next couple of lectures. Thank you.